Hello everybody and welcome to our first lesson in Unit 6 on right triangles. Today's lesson is about the Pythagorean theorem and its converse, and our objective for today is we will use the Pythagorean theorem to find the length of sides of right triangles and use the Pythagorean converse to classify triangles into acute, obtuse, and right triangles. So the Pythagorean theorem is something that we have discussed earlier this year already when we talked about the distance formula, and it works strictly for right triangles only triangles that have a right angle, and we need it, or we can use it when we need to find side lengths. Let's look at a right triangle. And when we name its sides, the hypotenuse is the side that's across from the right angle. Think about that right angle symbol and imagine it being an arrow that points towards the hypotenuse. And the hypotenuse is the side that we always call C. And the other two sides are the legs, which are adjacent to the right angle. Those sides get the names A and B. And in that sense, it doesn't matter which one of the legs gets the name A and which one of the legs gets the name B, but we always have to name the hypotenuse C. And then our Pythagorean theorem goes like this: C squared is equal to A squared plus B squared. Let's look at an example before we come back to our Pythagorean triples. Solve for x in each right triangle and simplify the answers. X is this side here, and if we look at our right angle, then we realize it points towards x. That means that x is really our hypotenuse, in other words, our C. So using the Pythagorean theorem, C squared is equal to A squared plus B squared. A squared is 12 squared plus B squared is 5 squared. And again, it doesn't really matter since we're adding here whether you think A is 12 and B is 5 or B is 12 and A is 5. Doesn't make a difference. Okay? So x squared is equal to 12 squared plus 5 squared. In other words, x squared is equal to 144 plus 25. X squared is equal to 169. So now let's take the square root of both sides, and x is equal to 13. Now this triangle has three sides with three nice integer side lengths. We got 5 and 12 and 13. And 5, 12, 13 is one of the so-called Pythagorean triples. A Pythagorean triple is a set of three positive integers that satisfy the Pythagorean theorem. And by satisfy, we mean make it work. If we plug those three numbers in, then we get a right answer for the Pythagorean theorem. The smallest and most common Pythagorean theorem is the numbers 3, 4, and 5. we have just now learned another one, 5, 12, 13, and there are an unlimited number of Pythagorean triples. 7, 24, 25 is another one, 8, 15, 17, and you can keep going like that. Specifically, we can take any of these ones that we have here and multiply each of the numbers by the same number and get another triple that also works. For example, we can multiply each of these numbers of our first Pythagorean triple by 2 and we get 6, 8, 10. That also works. Or we can keep multiplying by other numbers and the triples that come out are always going to be Pythagorean triples. Now these first four you should go ahead and memorize, because when we memorize the most common Pythagorean triples, then we get those answers much more easily and quicker than having to go through all the math. So make sure to memorize these four and understand that from these four you can derive an unlimited number of more triples by just multiplying each of the numbers by the same factor. Let's look at our next few examples and see how it works out. In number 2, we are given the two sides 12 and 16, and we are looking for the hypotenuse. So we have indeed two legs given. The hypotenuse is what we're looking for. 12 and 16 are not numbers that we have seen up here in our Pythagorean triples. But if we look at those numbers a little bit more closely, we realize they can both be divided by 4. So let's see what that gives us. That gives us 3 and 4. And now we got 3 and 4 for our two legs. And we can now realize that this is part of the first Pythagorean triple that we discussed earlier. So 3, 4, 5. If we multiply each of these by 4, we get our 12 and our 16 back, and we get 20 for the length of the hypotenuse. So x is equal to 20. And was this a Pythagorean triple? Yes, it was. On to our next example. Here we have the numbers 12 and 9. So will the three side lengths be another Pythagorean triple? We do have the two sides 9 and 12 that can be reduced to 3 and 4. However, realize that 12 is the length of the hypotenuse and not the length of one of the legs. So x is one of the legs that we're looking for. So 3, 4, 5 doesn't work here because the hypotenuse has to be the longest side. This one with 12 is the longest side. So the answer is no. We have to go through the math this time. So let's set up our equation. C squared is equal to a squared plus b squared. 12 squared is equal to x squared plus 9 squared. 144 is equal to x squared plus 81. Now we can subtract 81 from both sides, and we get 63 is equal to x squared. Taking the square root of 63, and the square root of 63 is not a perfect square, but it does have a perfect square in here, which is 9. 9 times 7. Square root of 9 times 7 is equal to x. In other words, 3 times the square root of 7 is equal to x. And this is the length of the missing side. On to our next example. Is this a Pythagorean triple? We see that one of the side lengths is an irrational number, not an integer, so the answer is no. we have to do the math that set up our equation, and I'm going to keep writing the formula every single time. C squared is equal to a squared plus b squared. So we keep practicing it and memorizing it too. 6 squared is equal to x squared plus the square root of 2 times the square root of 2 squared. In other words, 36 is equal to x squared. Now, how are we going to square 2 times the square root of 2? We can think of it as 2 times the square root of 2 times 2 times the square root of 2. And we get 36 is equal to x squared plus 2 times 2 is 4. Square root of 2 times square root of 2 is 2, so 4 times 2. In other words, 8. 36 is equal to x squared plus 8. Subtracting 8 on both sides, we get 28 is equal to x squared. Now we take the square root of both sides. 28 is not a perfect square, but it is 4 times 7. So the square root of 4 times 7 is 2 square roots of 7, and that is equal to x. In example 5, we need to find x again, but in order to do that, we also need to know the length of this leg, which we don't have. But this leg is also part of another triangle, which is also a right triangle, with the remaining side lengths of 25 for the hypotenuse and 24. Now, if we remember that 7, 24, 25 is one of our Pythagorean triples, then we can figure out that this side length has to be 7 without even doing the math. Otherwise, we would have to do the math to find this side first. But now we can go ahead and find x. X squared is equal to 7 squared plus the square root of 26 squared. Squaring and square root cancel each other out, and we get x squared is equal to 49 plus 26. In other words, 75. And the square root of x squared is equal to the square root of 75. 75 is not a perfect square, but it's 3 times 25. So x is equal to 5 times the square root of 3. And there is our answer. In our last example, we're supposed to find the length of the diagonal of the square. In other words, we're talking about the line that goes from this vertex to the opposite one. Well, what does the diagonal have to do with the Pythagorean theorem? Let's realize that if we have a square, we have 4 right angles. One of them is actually the only one that we are concerned about right now. And having that right angle, we have a right triangle. And better even, that right triangle, because it's inside of a square, has 2 legs that have the same length. Now 2 legs with the same length of 5, that is not a triple, so we have to do the work. In other words, looking for x, which in this case is diagonal, x squared is equal to 5 squared plus 5 squared. X squared is equal to 25 plus 25, or in other words, 50. Again, 50 is not a perfect square, but we had these perfectly fine perfect squares of 25 in there, and that means x squared, or the square root of x squared indeed, is the square root of 2 times 25, right? 25 plus 25, that's 2 times 25. And so x is equal to 5 times the square root of 2. And that's that. Well done. Now go ahead and watch the second part of this tutorial where we will talk about the converse of the Pythagorean theorem.